Welcome to this video. And in this video, I'll look at the time domain analysis of control systems. We look at time domain analysis of control systems. In time domain analysis, time is the independent variable and the response of the system is the dependent variable. In other words, we're interested in looking at the variation of the system's response or output with time. The response of the system varies with time and is called the time response of the system and can be divided into two parts. The first part is what we call the transient response. And the second part is what we call the steady state response. The steady state response of the system. Transient response is the variation of the output during the time it takes to reach its final value. So the variation of the system's response before it reaches the final value is called the transient response of the system. Then the steady state response of the system is the final value attained by the system or the final output achieved by the system. We can illustrate this in form of the plot of the system's response as a function of time as follows. If we sketch the output of the system y of t as a function of time, in some systems would have, as we'll realize later on, a response that looks like this. So the system's response grows exponentially and settles to a steady state value after some time. So during this period, before it gets to the final value or a steady state value, this is what we call the transient response. The whole of this response is a transient response because the system's response is changing with time. Then when it attains the final value, then we call that the steady state response of the system because the system's response does not change with time, but remains as a constant. And therefore, the system's response can be divided into two categories or into two parts. The transient response, which is the response that varies with the time, and the steady state response, which is the final value attained by the system. In any given system, of importance is the variation between the desired final value and the actual final value achieved by any given system. And that difference gives us what we call the steady state error of any given system. Therefore, the variation from the desired value and the actual value attained by the system is what we call the steady state error of any given system. Let's look at the steady state error. Steady state error. So the steady state error is the difference between the desired output and the actual output of the system and is denoted by error E and then subscript SS of T for the steady state, subscript SS for the steady state. And this is the steady state error of any given system, which is the difference between the desired and the actual output of the system. We consider a closed loop system defined by the following block diagram or represented in the following block diagram. We consider this closed loop system where R of S is the input, Y of S is the output, and the difference between the feedback and the input to the system is our error. From this block diagram, we notice that the error signal E of S is the difference between R of S and feedback B of S, where our feedback is our B of S, which is the same as the error signal minus the feedback signal is a product of the output and the feedback element, which is H of S, Y of S. That is our error signal. Also, we notice that the output of the system Y of S can be obtained from the product of the open loop transfer function and the error signal as G of S, E of S. If we will substitute for Y of S into the error, that is the steady state error equation, then our steady state error equation can be written as E of S is equals to R of S minus H of S, G of S, E of S. If we collect the like terms together, we notice that E of S into 1 plus G of S, H of S will be equal to R of S, from which the error signal E of S will be equal to R of S over 1 plus G of S, H of S. And this is the equation that defines the error signal E of S in terms of the input and the system defined by G of S, H of S. We therefore notice that the error of our given system, E of t, will be obtained from the inverse Laplace transform of E of S as the inverse Laplace transform of E of S to obtain our error E of t. From this, we know that the error in time domain analysis or in time domain, the error signal, which we have defined as the inverse Laplace transform of E of S. In time domain analysis, the steady state error is obtained by evaluating the limit as t tends to infinity of E of t. The steady state error is obtained by evaluating the limit as t tends to infinity of the error signal E of t. And applying the final value theorem in Laplace form, then in Laplace form, the error, steady state error, will be defined by the limit as S tends to 0 of S, E of S, which is the same as the limit as S tends to 0 of S multiplied by R of S over 1 plus G of S, H of S, since our error has already been defined by R of S over 1 plus G of S, H of S. And this is the steady state error in S domain or in Laplace form, which is obtained by the limit as S tends to 0 of S multiplied by R of S over 1 plus G of S, H of S. From this expression of the steady state error, we notice that the steady state error depends on two things. One, it depends on the type of input. It depends on the type of input R of S. The steady state error depends on two things. One, the type of input R of S, and also depends on the type of system. Depends on the type of system defined by G of S, H of S. And these are the two parameters that affect the steady state response or the steady state error of any given system. That is the input R of S and the type of system defined by the product of G of S, H of S. We proceed to analyze the steady state response of a first order system. We analyze the response of a first order system. The first order system is its highest power of s in the denominator as 1 and can be represented in block diagram as follows. So this is a negative feedback first order system. The open loop transfer function of the system is defined by 1 over Ts, where T is a constant. And for ease of analysis, we assume that the system has unity feedback. So we assume the system has unity feedback for ease of analysis of the response of the first order system. From this system, or the representation of the first order system, we can obtain the closed loop transfer function of the system, y of s over r of s, which will be equal to g of s over 1 plus g of s h of s, which is the same as our g of s is 1 over ts over 1 plus 1 over ts, and h of s is 1, which will be equal to 1 over ts plus 1, which can also be written as 1 over t over s plus 1 over t. So this is the closed loop transfer function of the system. Suppose we subject the system to a unit step input. If we subject the system to a unit step input, if the input of the system is a unit step input, that means r of s will be equal to 1 over s, and therefore our y of s will be equal to, so from the equation of the closed loop transfer function, y of s will be the closed loop transfer function multiplied by the input r of s, which can be written as 1 over t over s into s plus 1 over t. We can decompose this into partial parts, into two parts, as a over s plus b over s plus 1 over t, where our a will be equal to 1 over t over s plus 1 over t when s is equals to 0, which will be equal to 1. Our b will be equal to 1 over t over s when s is equals to negative 1 over t, negative 1 over t. And from this, then our b will be equal to negative 1, from which now our y of s can be written as 1 over s minus 1 over s plus 1 over t. The response of the system y of t will be the inverse Laplace transform of y of s, which will be equal to, so 1 over s will give us 1 minus exponential negative 1 over t. And this is our response for the first order system. The response of the first order system y of t has been obtained as 1 minus the exponential negative 1 over t. If we sketch this as a function of t, so when t is equals to 0, our response will be equal to 0. And as t approaches infinity, the whole of this term, the exponential term, will approach 0, and our y of t will be equal to 1. And this means then the response of the system is an exponential growing curve that approaches 1. And this is the response of the first order system. And as you can see, the response of the first order system is an exponential growing curve that approaches 1. We extend our analysis to the analysis of second order systems. Analysis of second order systems. analysis of second order systems. For a second order system, we'll notice of two important terms of a second order system. Number one, a second order system will have a term that we call the natural frequency of oscillation. Natural frequency of oscillation defined by omega subscript n. So the natural frequency of oscillation of the system defined by omega subscript n. And this is the frequency at which the system's response oscillates with oscillations of constant amplitude and frequency. The frequency at which the system's response has constant amplitude and frequency. So these kind of oscillations. So the amplitude is constant. If this is our response y of t, and this is our time, this is the period. And from the period, we can obtain the frequency of the system as the natural frequency of oscillation of the system, so long as the response of the system has oscillations of constant amplitude and frequency. Number two, the second order system will be subject to a second parameter called the damping factor. Damping factor denoted by zeta. The damping factor is basically a factor that tries to reduce the oscillations of the given response. And therefore, this will be a factor that does damping or opposes the oscillatory behavior of the response of the system. The general transfer function of a second order system is denoted by y of s over r of s is equals to omega n squared over s squared plus 2 zeta omega ns plus omega n squared, where omega n is the natural frequency of oscillation and zeta is the damping factor as discussed previously. So this is the general transfer function of a second order system. Suppose we subject the system to a unit step input. If the system is subjected to a unit step input, then we notice that our R of S will be equal to 1 over S, and therefore the system's response Y of S will be equal to omega n squared over S into S squared plus 2 zeta omega ns plus omega n squared. If we are to obtain the response of the system in time domain as y of t, we need to obtain the inverse Laplace transform of y of s such that our y of t will be equal to the inverse Laplace transform of y of s. And if we try to put this into partial fraction form, we notice that the damping factor will influence the nature of the solution of the partial parts of y of s. In the first case, zeta can be equal to 0. Zeta can be equal to 0. And this is a system that we defined as an damped system. This is a system that is undamped. If zeta is equal to 0, then the system is undamped. Number two, zeta can be between 0 and 1. So zeta is between 0 and 1. So we can write this as zeta is a number between 0 and 1. And this is what we call an underdamped system. An underdamped system. Number three is when zeta is equals to 1, and this is called a critically damped system. When zeta is equals to 1, we call that a critically damped system. And lastly, when zeta is greater than 1, we call this an overdamped system. So the response of each of the systems, depending on the value of zeta, will be different. And in my next video, I will discuss the second order systems response with respect to the different types of second order systems, the undamped, underdamped, critically damped, and overdamped system. Otherwise, that is the end of my presentation. And in my next video, I'll be discussing the systems response for second order system with respect to the four categories. Otherwise, thank you for watching this video.